Recording. There we go. All right. So we are going to talk about, in 1.4, we're talking about basically functions and their graphs. And we're talking about shifting, reflecting, and stretching. You can see that at the top. So this section is kind of just a interesting little FYI about how can we affect a function and change where its position is on the coordinate plane. All right. So I kind of think of this as a fun, well, you know, all math is fun, right? But no, this is a fun chance for you to kind of get into your graphing tool and to see, oh, okay, if I do this to my original function, what exactly happens to my, what happens to my graph? So I think this is a good kind of place to play with your graphing calculator, if you want to say that. So what we're going to talk about is, first of all, I think we went over these on Monday, but I just wanted to remind everybody what kind of these parent functions are. So let's flip into Desmos. One of these is Desmos. This has Desmos. There we go. Oh, that's not the one I wanted. But we can delete that off real fast. So you can do this in Desmos. You can do this on your TI-84 calculator. This would be under your Y equals button. Desmos does actually let you put in function notation, so if you really like to do that, you can. But for graphing purposes, it could also be a Y there. So Desmos lets you do Y equals X squared or F of X equals X squared. Either one's okay. So the first thing I wanted to do is just talk about the different functions, because we reviewed these really fast, but if you have your graphing tool with you, like if you have it on your phone, or Adam, you have it on your nice iPad or whatever you have, or if you have your TI-84, you can just be putting these in at the same time as I am and just kind of playing with it and seeing, oh, okay, what does that look like? So just kind of a reminder of our parent functions. So the first parent function is Y equals C. Now that's not really going to help us out. Well, I guess it did graph something here. But when they say C, they just mean a constant number. So let's just pick a nice easy one. So Y equals 5. So that's a constant function. So if you see any functions that just equal a number, in your brain you should be able to think, oh, okay, that's a constant. It doesn't change over my X values. The function's always the same. So that's kind of the most basic graph, right? And then the second function that we want to talk about is the identity function, which is also known as a linear equation, right? And this is just our Y equals X or F of X equals X equation. This is one of those standard equations. If somebody says Y equals X, you should be able to picture this in your brain kind of straight away, right? It's, if X equals 3, Y equals 3. If X equals -5, Y equals -5. So that is our identity function. Also, that's, our linear function. Those are kind of two in the same. Then we get a little bit fancier and we have our quadratic function, which is our fun parabola. Right, we got our parabola shape there. And in Desmos and also on your TI-84, if you've got a bunch of graphs, you can pull them up together. And then in Desmos, you can unselect the ones you don't want to be visible in your plane by going here. On your TI, you would just go to where the equal sign is and unselect the equal sign. And I can show you that too. We've got our cubic function. That always looks a little bit fun. Nope, cubic would be 3. We have our absolute value function. So in Desmos, they have a little absolute value here. So kind of what's interesting about absolute value. Oh, there we go. What's interesting about absolute value is that the value of our function is never negative, right? We always have a positive output value. And that's due to absolute value, right? You can never evaluate an absolute value and get a negative number. If I put in -5, the absolute value of -5 is +5. So I'm never going to have a negative value of my function. And then the last kind of one that they want us to just recognize pretty easily is the square root function. So this one is a little special too. That's not what I meant to do. Like I said, you can be playing with these on your calculator too. It's okay. So what's interesting about the square root function is that our x values can never be less than 0. Yeah, less than 0. They can never be negative, right? And so why is that? Well, that is because if I put, for example, -1 inside my square root, if you remember this from Algebra 2 at all, we can't have a negative inside a radical. We can't have a negative inside of a square root or cubed root. Well, we can, but then that puts us into imaginary numbers. And we'll get to that later. But in terms graphically, you know, that's a no-no. In terms of real numbers, we can't have a negative square root. So that's why you'll see that for this function, the domain has to be 0 or greater. So that's just kind of a review of the functions. Now we're going to talk about what we can do to the functions. So we're going to pick one of these. It doesn't matter which one it is. And we are going to just basically play with it to know, all right, how can I shift this particular function around when I do certain things to the function, how does it shift the graph, basically? So Jennifer, I saw you kind of were around this absolute value one. Let's do the absolute value one. That might be kind of fun. I don't know if you were pointing to that or not, but your cursor just happened to be there. So let's go with the absolute value. Okay, so this is the standard graph of an absolute value function. We'll delete all these other guys. Okay, so we are able to, what I'm going to do in Desmos is I'm just going to copy this because I'm kind of like, don't want to have to keep typing it. Okay, so what happens if we, let's say, add 2, if we add 2 to our original function. So our original function is the absolute value of x, right? F of x is the absolute value of x, and we have that nice green graph here. What happens if we add 2 to the original function? So you see the original function stays in place, but we add 2. So it looks like the whole graph shifts up 2 units, right? So that's pretty cool. So what do you think happens if we subtract? Yep, exactly, Jennifer. What do you think happens if we subtract 1? Before I type it in, because it'll go right away. So just think in your head, when I subtract 1? Exactly, it goes down 1 unit, right? Oops, I got to turn the graph back on so we can see it. It goes down 1 unit. Say we're making art, right? Now, so when we add outside the function, we're basically shifting the graph vertically, up and down, okay? What happens if we actually add inside the function? All right, so what happens if, let's hide this for a minute. Inside the function, I add 2. Oh, that's fancy. So when you add inside the function, you're actually shifting it horizontally. So you're shifting it left and right. This one is not quite as intuitive. So if you remember when we added 2 outside the function, we're making pretty pictures, right? When we added 2 outside the function, our function shifted up 2 units. So like adding 2 and going up 2, I think is more intuitive. When we actually add inside the function, it's a little less intuitive because when we add 2 inside the function, it actually shifts the graph to the left. So I think, I don't know, my intuition would say, oh, I'm adding 2 inside the function, so it should shift to the right 2 units, but it doesn't. Hey, Aiden. We're just going over 1.4. And then, no surprise here, what happens if I take this graph and I shift it, and I subtract inside the function? So I subtract 3. So if adding inside the function shifts it to the left, subtracting inside the function will actually shift it to the right. Okay? And then there's two more things that we did not talk about, but the other two things are reflections over the coordinate axis. Okay, so what does that mean? That means I'm going to go back to my original function. My f of x equals the absolute value of x, right? Here's my nice pretty graph. What if I wanted to reflect this about the x-axis? So this is going to be my reflection line, the x-axis, right? If I want to reflect it across the x-axis, type it there. I'm actually going to do a negative of the function. So you can see that the negative of the function causes a reflection of the x-axis. And then what if I wanted to reflect it on the y-axis? So my y-axis here. So in order to do a reflection on the y-axis, you're actually going to put the negative inside the function. In this particular case, it's not super interesting because the reflection on the y-axis looks like our original function, right? And that's because our original function actually already has a reflection about the y-axis. All right, has everybody seen this before? Yep. Does that make sense? Ish. Okay, so one more thing that I wanted to mention, since we have all these pretty, but let's throw them all up there at once. Can make some artwork on Desmos. All right. One of the things I wanted to mention is that these are all called, so horizontal shifting, vertical shifting, reflections, they are all called rigid transformations. So just think about that word rigid. Rigid means not changing, right? Our original graph remains intact. It's just being shifted where the points are on the coordinate plane. So we're not stretching the graph out or shrinking the graph at any time. If we want to talk about changes that cause distortion, we're talking about non-rigid transformations. Okay, and so an example of that would be, let's take all these off, go back to our original guy. So an example of a non-rigid transformation would be, let's take our original function, okay, and let's multiply our original function by 3. Okay, so what you can see when we multiply or when we divide, that's when we get our non-rigid transformations. So that's when we get that distortion where our graph, our original graph isn't just basically moving around the coordinate plane, but it's getting distorted. It's either, has a greater slope, greater value, it's slowing down, that type of thing. So when you're dealing with adding or subtracting inside the function or outside the function, or making negatives inside or outside the function, those are rigid transformations. So your original graph is going to stay the same. When you deal with multiplying and dividing, that's when you're going to get some stretching or some shrinking. And that all just depends on which number that you do. Okay. Does that sound good? It's exciting, right? Awesome. Any questions about that? We can do like a couple examples from your notes, but I think, or from from that section, but I think you guys are going to really, really breeze through this really quickly. So I know you guys are very cheerful. It's like me talking to myself. But you're at least nice on the chat. So I will take that any day. So let me just pull up here. These are from your notes. We're not going to do all these because like I said, I think it's intuitive. And I think the cool thing is that you can take your calc. That's not what I wanted to do. Sorry. I did print screen. I think the cool thing is that you can take your calculator and you can play with it and see, oh, okay, that's what that does. You don't have to graph everything by hand. Now, if you had to graph everything by hand, then it might be a little bit of a pain. Right? Okay, so let's do maybe like one or two of these. I think you guys are going to pick up on super quickly. So for example, in 1 through 12, so you're going to do 1 through 11, it says, sketch the graph of the three functions by hand on the same rectangular coordinate system. Verify your result with a graphing utility. So I'm not expecting these to be like the perfect graph, right? The other thing that I have done before, and I haven't sent it out to you guys yet, but if you want to get some graph paper, you're welcome to do that if that makes it easier for you. There's also tons of free printable coordinate planes. I know you guys have all been searching Google for that all the time. But if you look for that, or I can send you ones that I've downloaded before, there are places you can just print off, a sheet, and it has 10 coordinate planes already pre-printed for you sitting on there, and then you can just draw right on there. If you just like to draw by hand, that's okay too. But I just wanted to mention that so you're not taking, a ton of homework time drawing out beautiful coordinate planes for me. All right, so let's try. That doesn't matter to me. Well, we kind of just did absolute value, so we don't want to do 10. So let's do number 6. All right, so number 6 is we have f of x, g of x, and h of x. Okay, and so probably just helps to think, what is our original parent function? So off to the side here, I know that f of x, or y, equals x squared. Yep, Aiden's got it. He popped up already. It's a nice parabola, right? Looks something like this. It's a pretty little parabola. Okay, so what happens if we have, let's look at f of x. F of x is x minus 2 squared. So I have to think about it a little bit. Where would that be? So what's happening to f of x is that we're subtracting 2, and it's inside my function, right? Because it's inside the square term. So I know it's going to shift on the horizontal axis because it's inside of my function. And I know it's going to be 2 units, but do you guys remember, is it going to go 2 units to the left or 2 units to the right? This is my beautiful graph here. All right, I have a couple of people saying 2 units to the right. So because it is negative and it's inside the function, you guys are all correct. And I saw, Jennifer, I saw your little cursor on there too. So it's going to shift over here. Now, is there anything else being done to f of x? No. So I'm just going to go ahead and draw my beautiful parabola right here. And we're going to label that f of x off the screen. Just give ourselves a little more room here. There we go. That's f of x. All right, so now let's move on to g of x. So g of x has 2 things going on with it, and they both involve 2. All right, so g of x has the plus x inside, and it has a plus x outside. So that actually kind of works out nicely for us, right? If you're really confused on a test, you might not need to remember. So the g of x with the inside plus 2 is going to shift our graph to the left 2 units, right? So we know that we're over here because of the shift inside, the horizontal shift inside. But then we also have this plus 2 on the outside. Sorry for my lovely drawing here. So the plus 2 on the outside is actually going to shift up or down. What do you think? Up, up, and I see Jennifer's, yep. So that's going to shift up to here. So if I graph g of x, whoa, I don't even know what color that is. I don't even know how I picked that. It's going to be up here, right? And I know this is just lovely drawing, right? All right, so h of x is our tricky one. It's our kind of our brain twister. So, oh, I heard somebody talking. So we got a couple things going on, right? What I like to do is I like to look, kind of work my way inside out, but you can have different ways that you might want to do this too. So we have inside of our function, we have minus 2 again, which means that our kind of our center point is going to be shifted over here. All right, can you see where my blue mark is? Over here. All right. And then we have negative 1. So that means that our graph is going to shift down negative 1. But wait, there's more, right? What about this negative sign out front? How's that going to shift or change our graph? It's not going to shift it horizontally or vertically, but it's going to be a reflection. Is it going to reflect on the x or the y axis? What do you guys think? I think it's going to be about the x-axis because it's outside of our function. We've got the negative sign outside of our function. If it was inside of our function, something like that, then it would be reflecting across the x or the y-axis. But because it's outside of the function, it's going to be reflecting about the x-axis. So all that to say, that's a sad-looking parabola, pointy parabola. There we go. Get our pointy parabola there. And then if you can go back to your original problem, if you type all these into your graphing tool, it'll pop right up for you, right? Just good to kind of check and say, oh yeah, I can do this. Okay. 16, 18, and 20, you're basically going to look at the graph and you're going to try to write what do you think the function for that graph would be. So really quickly, let's look at number 18. And it's really tiny on your screen. So you guys thankfully have little eyes, right? Not little eyes, young eyes. You guys have young eyes. And you also have your book that you can look in better than I do. So just looking at 18, what is the parent function for this? What's the function that this is based off of? Oop, anybody? Nice. Jennifer says absolute value function. I agree with you. This is a absolute value function. I'm sure you guys all are like, yeah, we got that, right? But something's happened to it, right? It's shifted. It looks like it is shifted to the left, and my eyes say 2 units. 2 units to the left. All right, so if I'm shifting to the left 2 units, I'm shifting horizontally 2 units, is that going to be inside of my function, or is it going to be outside my function? Yep. See, you guys all got this. F of x. Nice job. Nice job, Aiden, Adam, and Jennifer. Plus 2. So because I'm shifting 2 units to the left, and it's on the horizontal shifting that I'm doing, it's going to go inside the function. And it's that opposite one. Okay, I think I can set you loose on the rest of the homework, especially if you look here, 22 through 34, it just basically says, compare the graph of the function with the graph of f of x equals the square root of x. So basically all you're doing for these is you're going to, compare the original parent function to these shifts to kind of see, oh, okay, if I, add 2 outside of the radical versus add 4 inside the radical, what does that exactly do to my function? And then just do a quick sketch of those. So I think you guys are going to rock. This homework should be nice and easy. We all like that, right? Yay. Hey, Aiden's talking to me. I'm glad I can hear you. All right, so we're actually going to go on to 1.5 too, because if we've got time, we're going to plow through it so that when we get to the sections that are difficult, we have a little bit more time. So I think 1.5 is a fun section if you like doing like all the manipulation of algebra, like you like to sit there and, go through all the steps of combining things together. 1.5 also looks slightly intimidating if you've never done it before, but it actually is not as difficult as it seems, I believe. Okay, so let's, without much further ado, thanks. Let's talk about combinations of functions. Okay, so I think honestly, the terminology looks a little bit more complicated than, oh, there we go, we can make it bigger. The terminology looks slightly more difficult than what we're actually going to be doing, especially for sum and difference, okay? So let's say we have 2 functions, f of x and g of x. We can actually find the sum, the difference, the product, and the quotient of those 2 functions. So if we have, let me take a super duper easy example. I guess I need to print screen here. All right, let's take some really, really easy examples. Let's say f of x equals x, and let's say g of x equals, let's just do really easy. No, g of x equals, I'm just trying to decide, I might just want to do a constant. Yeah, let's just do a constant. G of x equals 5. There we go. All right, so if I wanted to find f plus g of x, that simply means that I'm going to add f of x plus g of x. So if I wanted to evaluate f plus g of x, what that practically means is I'm going to add f of x, which is x, plus g of x, which is 5. And this would give me f plus g of x. Now, obviously, our functions will be a little more complicated than that, but that's really all there is to it. So what do you think if I wanted to find the difference between f and g? What do you think that's going to look like? That's simply the difference of function f from function g is simply f of x minus g of x. Okay, so remember my f of x is x and my g of x is 5, and that's it. That's the difference of my 2 functions. Oh yeah, you got it. I see it down there, Jennifer. Difference can get a little bit tricky because if you have a more complicated function, you just need to remember to subtract the whole function. But it's not too crazy, right? What about the product? If I have f of f times g of x, guess what I'm going to do to my two functions? I'm going to multiply them together. Takes me longer to write them out than to actually do it. So f of x times g of x is just 5x. And then you get the idea. If I want to divide f of g of x, I'm going to divide, nope, not 5 on the top. X is going in the numerator, and 5 is going in the denominator. So this is just fun. You know, these functions are so awesome. Why not add and subtract them together, right? Just make them even more fun. Am I convincing you how awesome it is? Nope. It's not terribly complicated though, right? No, it's just a fancy way of saying that. Okay, then the one thing that gets a little bit trickier, but still you guys are going to be completely fine, is called a composition. Okay, so this is when you actually put one function into another function. And we actually did a little bit of this a few sections ago, but we didn't call it a composition. But you can actually do something called, well, a composition, and you would say f composed with g. And so when you see a function with this little dot here, that is known as a composition. So basically that means that you're plugging one equation into the other equation. And we've had experience with this before, like, I'm trying to think of the application. I know in Algebra 2, when you have a system of equations, like you have two variables and two equations, then we plug one equation into the other to get rid of a variable. So you've actually done this before in other applications. But what we're going to do is we're going to take, I wish I had a little more room here. I'll just make a little room. Fill that in with, there we go. Just make our own little box there. So for this example, it's pretty easy. So if we have f composed with g, that's not what I wanted. F composed with g, basically we're going to substitute g of x as our x in f of x. That totally made sense, right? But when you see it, it'll make sense. So we have f of g of x. Okay, so we'd start with our original function, which is f of x equals x, right? But instead of x, we're going to substitute in our value of g. So this is actually kind of oversimplified, but we're going to put in f of g of x, and we know g of x is 5. And then if we look at our original function, f of x equals x, so f of 5 would be 5. This was not a great example for that, but we will do some more compositions so you can kind of see how we substitute one into the other. Aren't you guys excited? So fun. Can't contain your excitement over the phone. I'm sorry, guys. I know, this is awesome. It's actually fun if you like to sit there and work through all the math stuff. All right, so let us do an example or two, just so you can kind of see with, you know, a little more complex functions than what I put out there. Let me grab a screenshot from that. Does anybody have any questions? No? All right. You guys are like my chill class. Let's do this. I don't even need all that. All right, so this is basically what we were doing before. So they're giving us some functions. We got f of x and g of x, and they want us to find what is the function when you add them together, what is the function when you subtract them, multiply them, or divide them, all of those fun things. And then they want us to tell what is the domain of f of g. So we'll talk about why they ask that question as well. Does anyone have a particular one that looks fun? They all look fun, I know, it's hard to choose. Let's do 10. Because why not, right? So what if I wanted to do, let me get my paper up here. What if I want to do number 10, right? So the first thing they want me to do is f plus g of x. So if you remember, when I have f plus g of x, it's going to take me longer to write these than to do them. And you guys can try these on your own too, right? F plus g of x is just simply f of x plus g of x. So I have the square root of x squared minus 4. This is my f of x. Plus x squared over x squared plus 1. That's my g of x. Ta-da! Look at my lovely function. You could probably do some crazy things to simplify that, but let's just leave it like that. No, you could, yeah. We'll just leave it like that. So what do you think would happen if I did f minus g of x? It's going to look exactly the same, right? Except it's going to have a negative sign in there. So I won't put you through the pain of watching me write that all out, right? What about f g of x? Sorry. What about f g of x? What are we going to do there? So I'm skipping around. This was A. I think B you can figure out. C, we've got f g of x. So that just means I'm simply going to multiply my f of x times my g of x, right? So I have the square root of x squared minus 4 times x squared divided by x squared plus 1. So I can do a little simplifying there. I can just, put everything in the numerator together. And then we have our nice pretty equation. It's complicated stuff, right? That's why they call it Precalc. No, I think this is a nice, good section to end with today. All right, so what about f divided by g of x? What do you think you're going to do there? Divide. Yep, there you go. I probably, just because you've got this crazy fraction, instead of just writing a division problem, I'd probably just go ahead and multiply by the reciprocal. Of the g of x, right? Just so that you get, if you're dividing, you can multiply by the reciprocal and do the same thing with a fraction. All right, so that's that. I saw that, Aiden. All right, so what is the domain of f of g? Can we tell just by looking at this? Or sorry, I said that wrong. What is the domain of the function that is f divided by g of x? So we're looking at this last crazy combination that we did. When we talk about the domain of this, are there any restrictions about what's in our domain? For this particular one, there wouldn't actually be, right? Because you can put in any value of x in the denominator and you're still good. Where you have to worry is if, like for example, in this first example, f divided by g of x would actually be 2x minus 5. Oh, that's not what I meant to do. Over 1, sorry, my pen thinks I'm like scrolling my page. I apologize. All right, so for the combination of number 6, the domain would be all reals except when x equals 1. And why is that? Because when x equals 1, 1 minus 1 is 0, then we'd have a 0 in the denominator, and that's undefined. Okay? Makes sense? Okay, so let's do, yeah, so that's 1 through 12. You guys will be good with that. 13, whoa, that came out weird. 13. Oh, wait, Jennifer said, what about the 0 in the bottom on number 10? Yeah, so that's a good question, Jennifer. So in number 10, there is no 0 at the bottom because there's no value. Oh, thank you. You're right. We can't have 0. I don't know what my brain was thinking. You cannot have 0 as a value. So the domain would be all reals except 0. I was just thinking, oh, it's a square function. Everything should be good. But you are correct. All right, so let's do one more, and then that should kind of get us to the end of today. I mean, I know you guys are sad that this is over because it's so fun. But we're going to skip to number 36. But I think you should be able to tackle most of the other ones. If you have any issues with it, let me know. Oh, I know what I was going to say. 14 through 26, you're just basically you're taking the functions and you're doing whatever they say, and then you're actually plugging in a value for x. Okay, so for number 14, you're going to do f of x minus g of x, and you're going to find what that formula is, and then you're going to evaluate what happens when x equals -2. So for those, you're actually going to get a value. So going back to where we were, it's just basically plugging in a specific value of x and evaluating what that is. Okay, so 36 and 38 is where we get into the composition. Okay. Yay. Exciting. Yes, right here. So let's do number 36, and then we'll kind of talk about this because it's a nice segue into what we'll be doing on Monday to finish up the chapter. Okay. So we have, in these exercises, find f composed with g, g composed with f, and if possible, f composed with g at 0. Okay, so have you guys done compositions before? Everybody's so quiet. Okay, all right, so I just wanted to make sure I wasn't like boring, you guys. All right, so let's talk about f composed with g. All right, I actually like to, I think in my head, makes a little more sense when it's written out like this. That's just me personally. So what you're actually doing is your original f of x is kind of staying the same, but you're plugging in g of x for your values. So what is g of x? G of x is x cubed plus 1. Okay, so you're composing it by putting g of x into f of x. So this is basically like your value, your new value of x. So my original f of x is 3x minus 1, right? But since I'm composing it, I'm going to erase my x here. I'm putting g of x in for my value of x. So in here goes my x cubed plus 1. Okay, so can you see how you're putting g of x in green into f of x, which is in maroon? You're going to compose it together. So now is where kind of that algebra fun comes in, right? Because all algebra is fun. So we're going to just do a little bit of simplifying, right? So we have x cubed plus 1 minus 1. Well, that's nice. They cancel each other out. So we're left over with the cubed root of x cubed. That was really nice how they worked that out for us. So cubed root of x cubed would just give us x, right? So the composition f of f composed with g would actually just be x. All right. If we do, let's skip to part C. Can we do f composed with g at 0? Well, yeah, we can definitely do that, right? F composed with g at 0 is just 0. Fascinating, right? All right, so now let's see if I can, I took up too much room. I'm going to kind of erase a little corner here. So you're not going to get the whole picture, but I want to leave some of this up on here because we're going to talk about that. So let's erase a little corner while still leaving up the rest of our answer. Okay. So let's talk about now if we do, oh, well, sure, we'll just make a box there since that was what my thing was on. What if we do G composed with F? So we want, I should keep with my color scheme. We want G composed with F of X. Okay, so that means that we're going to do G, and F of X is the cube root of X minus 1. So that's the value that I'm going to plug into G. Okay, so my function G is X cubed plus 1. If I can get my pen to work. Okay, but we're not actually going to put in X, right? We're putting in F of X, which is the cube root of X minus 1, all cubed. Sorry, Jennifer, I missed your Y. Hopefully I explained what you're asking. All right, so if I talk about G composed with F, and then I have some simplification to do over here. So what is the cube of the cube root of X minus 1? Well, that's nice again. It just leaves us with X minus 1. If we evaluate the cube of the cube root plus 1. So we are just left over with X, G G composed with F also equals X. Now, I will tell you that not every composition works out this nicely. Okay, so if you do, which one did I do? If I did 38, I do not get the compositions both equal X. This particular problem just happens to work out that way. The reason I wanted to do this problem, and I know that I'm almost done with my time here, but the reason I wanted to do this problem is because it's like this perfect lead into 1.6. And we'll talk about 1.6 on Monday, but 1.6 talks about inverse functions. So we know about inverses when we just talk about, fractions, what the inverse of a number is. If you have 5, the inverse is 1 over 5. And the definition is that the number times the inverse equals 1. All right. So when we talk about functions, we can actually talk about the inverse of the function. Okay. And the definition of an inverse of a function is when you compose the two functions, when you do f composed with g and g composed with f, if they both have a result of x, then they are inverse functions to each other. So just kind of keep this in the back of your mind. These two are actually an example of an inverse function. And if I pull up Desmos really quick and clear everything off and type these two original functions in there, you'll actually visually get to see what two inverse functions look like. So you can use composition to figure out if we have inverse functions. So let me just type this in really fast and then we will be on our way. There we go. So we've got f of x is the cube root of x minus 1. Got some crazy graphs, right? And we've got g of x equals x cubed plus 1. Okay, so here are the two graphs that we just did the two compositions for, right? And when we composed them both ways, f composed with g and g composed with f, both those compositions resulted in that they equal x. And that's the definition of inverse functions. And then you can see when you graph them, they kind of look like this nice little, ooh, isn't that pretty? Right? They look like this nice little thing. And guess what? They reflect across our good friend y equals x. So they are a reflection across y equals x. So this is our line, and that's another, it is art. This is another representation of an inverse function. So I just thought it was kind of cool. We could do something in 1.5 that actually would tell us, oh, this is, when we get to 1.6, you'll be like, okay, I've seen this before. So that is an inverse function, and why we do compositions. We do compositions so that we can find out if functions are inverses algebraically, because it's fun. And it's pre-calculus, right? So that is it. Thank you guys for sticking with me today. I appreciate it. Thanks. I do have one super quick question. You can just type it back to me in the chat. We are almost done with chapter 1. So is having this big old packet of notes helpful for you? Would you rather just take notes on your own? Would you like a pared down version of this? Keep doing the same thing for chapter 2? I'm just trying to figure out what works well for everyone. So if you can just type back if you think it's helpful to have the big packet. If not, it doesn't matter to me. Oh, okay, good. Jennifer and Sarah say they like it, so. Oh, Aiden says, it's actually not too much work for me because thankfully you can find most of your textbook actually online. So it's just a lot of screen grabbing. Okay, awesome. Thank you very much for your feedback, guys. Have an awesome day. If you come across any questions, let me know, but we'll actually finish chapter 1 on Monday, which is awesome. So, thanks, guys. Have a good day. Bye.